This is a video for MEI Core Pure Mathematics, Calculus 3, Integration using partial fractions, 3.3, Integrating with a denominator that has linear factors only. It often helps to rewrite the integral of an algebraic fraction in partial fractions. Makes the integration easier. We need to check that the order of the denominator is greater than that of the numerator. And if not, then you do an algebraic division and integrate the remainder using partial fractions. And we'll have a look at an example of that a little bit later on. Once you've split into partial fractions, you can then split the integral up, and it can be handled as two or more separate integrals. Okay, here's an integral to look at. This is an algebraic fraction. We've actually seen this in a previous video. And in fact, x minus 9 over x plus 1, x minus 4 can be rewritten as 2 over x plus 1 minus 1 over x minus 4. So now what I can do is I can rewrite my integral. Here's my integral, x plus 1, x minus 4. I can rewrite that as the integral of this pair of fractions. So that's 2 over x plus 1 minus 1 over x minus 4. Okay, so I can integrate this as two parts now. The first part here, 2 over x plus 1, just gives me twice the log of mod x plus 1. And the second bit minus the log of mod x minus 4. And of course, plus a constant because we have got an indefinite integral. Now, as it stands, this is an answer, but it's not the simplest form of the answer. Remember that the 2 outside of the log here really means that what's inside the log has been squared. So we can rewrite that as the log of x plus 1 squared. And taking logs away means that we've actually done a division inside here. So this thing becomes the log of x plus 1 squared, because of the 2 outside, divided by x minus 4, because we're taking away this log. And of course, I need my constant of integration. There's that. Tied it up slightly for you. There's my partial fractions there. And then substitute that into the integration. And there's my final result at the bottom. Okay, this second example, I need to do a division check. If I look at the bottom line is actually x squared minus x minus 6. And the top line is 5x squared. So I'm going to divide the top line by the bottom and see what we get. X squared into 5x squared goes 5 times. So multiply that back across. I'm going to get 5x squared minus 5x minus 30. And if I take that away, I'm going to get left with 5x plus 30. So I can rewrite 5x squared over x plus 2 times x minus 3. I can rewrite that as 5, remainder 5x plus 30, and of course that remainder is over x plus 2, x minus 3. So this bit will integrate easily. This bit is an algebraic fraction that won't go any simpler, and so I'm going to need to look at partial fractions for 5x plus 30 over x plus 2 x minus 3. There's that little bit of working so far for you, just gone on through. There you can see your remainder for the integral, and so that's the partial fractions that I'm going to be interested in. Okay, let's do a little bit of work on that then. So starting from this point, 5x plus 30 over x plus 2x minus 3, split it into two parts, a over x plus 2 plus b over x minus 3. Multiply through by the denominator, and I'm going to get 5x plus 30 is identical to a times x minus 3 plus b times x plus 2. So looking at these, it looks like from here x equals 3 is going to be something to try. Okay, so here's x equals 3. What happens on this side? I get 15 plus 30 gives me 45. There is equal to, I get nothing from that bit, and I get 3 plus 2 is 5b from there. So that's going to give me that b equals 9. Looking at the other bracket here, minus 2 looks like a possibility to zero out that, so let's have a look at what happens when we put in x equals minus 2. I get minus 10 plus 30 is 20. I get minus 5a here and nothing here, so that's going to tell me that a equals minus 4. So my partial fractions for this bit are going to be that 5x plus 30 over x plus 2 x minus 3 is actually 9 over x minus 3 minus 4 over x plus 2. And notice I've switched those two around so I can keep the minus sign in sight, but I've still got a over x plus 2 and b over x minus 3. So now the integral that I'm trying to do, if you remember back from the last slide, I've got 5 plus 9 over x minus 3 minus 4 over x plus 2. So integrating that, I'm going to get 5x from the first bit, 9 lots of the log of mod x minus 3 from the second bit, and then minus 4 lots of the log of mod x plus 2 from the last bit. And don't forget my constant. Now, as we did before, we can combine these logs. So I could rewrite that as 5x plus the log. Well, this is going to be x minus 3 to the power 9. And that's going to be over, because I've got a minus here, that's going to be over x plus 2 to the power 4 plus my constant. Okay, so there's that working, tidied up for you. That's the partial fractions working through here to give me the partial fractions result, and that leaves me with that integral. And then there's the integration worked through, so I get the 5x plus 9 log x minus 3 minus 4 log x plus 2 plus c. And you can combine the logs as we saw on our previous slide. And either result is correct, and it's really only worth combining the logs for smaller powers. This one, frankly, you would question whether it was worth doing, but it can be done. Okay, so in summary, we check the denominator is a higher power than the numerator. In our second example, they had the same power, and so we divided through to get a value and a remainder. Split the algebraic fraction into partial fractions, and then split the integral up to handle it as separate integrals. In this case, for linear factors, you'll get logs in the result, and we saw that in both of the cases that we looked at. You get logs in the result, and they can be combined into a simple log. But this is really only worth doing if the coefficients are relatively simple. The next video in this sequence is integrating using partial fractions with a denominator that has a repeated factor on the bottom.